Chemists, in this lesson we are going to look at the Diels Alder reaction. This is a very famous cycloaddition reaction that was developed by Otto Diels and Kurt Alder. They won the Nobel Prize for this in 1950. And it looks like what you see over here in the box on the right. It involves two molecules as reactants, one called a diene, the other called a dienophile, which just means it likes dienes. The reagents are just heat. That's what that triangle means. And you always form a cyclohexene, a six-membered ring with a double bond. So let's take up the arrow pushing for this, some restrictions about those two reactants, and then some really interesting stereochemical consequences of the reaction based on the mechanism. So here's an example of a Diels Alder reaction. First, let me show you how you can figure out the product. I always like to number the carbon chain. In the diene, 1, 2, 3, and 4. And the dienophile, it's really only 2 atoms that end up being part of the new cyclohexene, so I'll call them 5 and 6. The arrow pushing for this looks like the following. Your diene is a nucleophile, and it attacks the dienophile. The dienophile pi bond forms a bond with the diene, and then this pi bond in the diene rearranges. So you get a 3 curved arrow, 6 electron transition state. So that gives me a new 6-membered ring, and it is made up of those 6 atoms we just numbered. So let's draw that. It looks like this. New pi bond between carbons 2 and 3. We have a methyl on carbon 2, another methyl in this case on carbon 3, and then I have this cyano group, a nitrile, on the ring in the upper right-hand side. And there's what they're called. That's the dienophile, and that's the diene on the left and the dienophile on the right. And I've already mentioned the diene wants to be electron rich. That's because this is the nucleophile. Conversely, the dienophile is electron poor. That's the electrophile. There is such a thing as an inverse demand Diels Alder where you switch that, but for the most part, this is what we're going to see. And it's easy to see at least part of that. Think back to the groups that are attached to rings in our aromatic unit. Something like a cyano group, that's electron withdrawing. So it makes sense that this would be a good dienophile group, E, W, G. And methyls are frankly a little donating, just at least through the inductive effect, electron donating group. Some features of the reaction, or some restrictions, I should say, of the reagents. Let's take a look at those. Number 1, the reaction is concerted. It is a 6-electron cycloaddition. Cycloaddition, I hope, is self-explanatory. 2 molecules add together and make a cyclic compound. What's the point of pointing out that it's 6 electrons? Well, that's those 3 curved arrows, but also you should recognize the number 6 as being a good number for Huckel's rule. 4n plus 2 is not just the number of pi electrons we want in an aromatic ring, it happens to make a very stable transition state. In fact, without even realizing it, we've seen lots of 6-electron transition states in this course. This is just another one. We're going to look at a few others in the next lesson in this unit, so stick around for that. Feature 3 of this reaction that I'll mention is that the diene and dienophile add syn to each other. We'll see that that results in a stereoselective reaction. We'll look at an example of that in a second. And lastly, some restrictions specifically about the diene. The diene must be S-cis. That's a new term for us, and it's what we refer to the conformation. It's how we describe a conformation of specifically a diene, where the 2 alkenes are pointing in the same direction. So that's an example of an S-cis diene, as is, let's say, a cyclic cyclohexadiene, and not S-trans, which is the name of the other conformation that you could imagine, where the 2 alkenes pointing off of a single bond in between are going in opposite directions. And you might go, what's the point? I could just rotate around that bond, right? Well, yes, you can for that one, but imagine having a cyclic molecule that's actually locked in an S-trans conformation. So this would be a terrible Diels Alder diene. This would be a fantastic Diels Alder diene as a result. All right, so let's look at some examples and see some stereochemical consequences of this. So we just said that this reaction occurs with syn addition, and that's true. And what that does is it takes specific alkene geometries and it turns it into relative stereochemistry in the product. So here's an example of a cis alkene with just a very boring butadiene diene. But the dienophile is cis. And how do I figure out the product? First of all, let's number our diene, 1, 2, 3, and 4, and our dienophile, 5 and 6. I like to draw dotted lines between carbons 1 and 6 and 4 and 5, because that starts to show me where my 6-membered ring is going to develop. So I get a 6-membered ring with an alkene between 2 and 3, and then I have a methyl ester and another methyl ester along for the ride attached to carbons 5 and 6, and I'll just fill those in. And you'll notice we created a couple of asymmetric carbons in this example, and it turns out that because the alkene we started with is cis, and because this reaction is a syn addition, those asymmetric carbons are syn to each other. So the cis alkene turns into the syn diastereomer. And that's because if you think about how this reaction works, your diene and your dienophile form those bonds all at the same time. This is a concerted reaction. You can think back to many other concerted reactions we've seen where there's additions that are occurring and they almost all have syn addition as a result. Hydroboration, hydrogenation, cyclopropanation. Those all have syn addition features to them because there's a concerted step in those mechanisms that involves the main formation of bonds in the products. So let's say instead of a cis alkene, I start with a trans alkene. Let me just label that. This is the trans alkene. And guess what you're going to get? You're going to get the anti-diastereomer. So what does that look like? Well, we still have the same connectivity, 1, 2, 3, and 4. There's 5 and 6 way over there. New bond between 1 and 6, new bond between 4 and 5. So we get a 6-membered ring. Alkene between 2 and 3. This time my methyl esters are not syn to each other, they are anti to each other. I'm going to abbreviate them as CO2 methyl. I could have drawn them in the plane of the page and showed the relative stereochemistry of the hydrogens as I did in the previous example, but it communicates the same information. It should be noted just one more thing about this particular example. That one up there happens to be a meso compound. This one is not a meso compound, so there's another enantiomer that I could draw with those methyl esters anti to each other, but I'm going to abbreviate that with just the plus minus symbol, meaning you will get a racemic mixture. You're not going to get anything enantiomerically enriched out of this. We started with achiral starting materials, so we're going to get an achiral racemic mixture in the end. Chirality has to come from somewhere, and we just don't have it in this particular example with the starting materials. Okay, so syn addition results in cis geometry becoming syn stereochemistry, and likewise trans geometry becoming anti-stereochemistry. What about if our reagents are not symmetric, as we've seen so far? This is a very symmetric diene and a very symmetric dienophile, but here I have an example with less symmetry in the starting materials. Here's a diene and a dienophile. Let me just figure out what one possible product might be. I'll do the same thing I've been doing. Number my diene, 1, 2, 3, and 4. Number your dienophile, 5 and 6. Let's draw some dotted lines between 1 and 6 and 4 and 5. And that potentially gives me a 6-membered ring with an alkene, an aldehyde down there, and then a methoxy up here. But I sort of arbitrarily drew it with the diene and the dienophile just matching up the way that they're drawn right there. What if I took my diene and my dienophile, but I rotated one of them on its head and then made a bond that way? That would give me a different product. Now let me just draw exactly what it would look like. Still be a 6-membered ring. Still have an O-methyl. Let's imagine keeping the diene locked in the same space, but let's turn the dienophile upside down. That means your aldehyde would be up here. These are not stereoisomers, these are constitutional isomers. Which constitutional isomer do I get? Turns out you get the one on the left as a major product, and it has to do with the fact that the diene and the dienophile are not symmetrically arranged in their electronic arrangement. So we said earlier that the diene is electron rich, and one of those 2 carbons on the ends is more electron rich than the other. Turns out it's the one at the top. Likewise, the dienophile is electron poor, and one of those 2 carbons is more electron poor than the other. Turns out it's that one. So the more electron rich carbon of the diene will attack the more electron poor carbon of the dienophile. And that should make you go, why is that carbon more electron rich in the diene, and why is that one more electron poor in the dienophile? Well, what's the answer to almost everything in organic chemistry? Let's look at some resonance contribution. If I redraw that diene, which has an O-methyl, there is a significant resonance contributor that shows donation from that methoxy's lone pairs onto the carbons, and you get a contributor that looks like this with a negative charge on the exact carbon that we just pointed out as more electron rich. Likewise, the dienophile, which was just acrolein, it's an alkene with an aldehyde attached, also has a resonance contributor that shows that that carbon is more electron poor. How can we show that? Think about electronegativity and dipoles. Oxygen is very electronegative, so there's a dipole toward the oxygen, and that pi bond can move over, and as a result, you get a positive charge on that carbon. So it's that positive charge character in the dienophile that matches up with that negative charge character on the diene, and that's why they line up in that arrangement as opposed to the other direction. Okay. Lastly, let's look at some more, one more example of the Diels Alder reaction, where again we have a little lack of symmetry, but you'll notice in this case we're going to create a number of asymmetric carbons. So first let me just show the possibilities. I'll number by diene 1, 2, 3, and 4. And I'll number by dienophile 5 and 6. I draw a bond about to form between 1 and 6, another one between 4 and 5. There's the beginnings of my 6-membered ring. So we make a 6-membered ring. Alkene between 2 and 3. I have an O-methyl, an O-methyl, and a methyl ketone. Now we already know that there's syn addition, and the alkene would tell us, the geometry of the alkene and the dienophile would tell us this relative stereochemistry, but this one up here isn't even an asymmetric carbon. So what's to tell me what the relative stereochemistry is between these 2 positions and this one? And frankly, you could imagine I could have a 4th one right there. It turns out that syn addition and one other feature make it so that all the possible diastereomers funnel into just a very small number. We don't get all the possibilities. With 1, 2, 3 asymmetric carbons, 2 to the n is 2 to the 3, and you have 8 possible stereoisomers? No, not in this case. Turns out there's only one diastereomer that's formed, and it's this one. It's with all of those groups actually pointing in the same direction. I'm going to give them all dashed lines as a result. No other diastereomer is formed. Now this is racemic, so they could all be going toward you as opposed to away from you, but I don't have mixtures of toward and away, all other possible diastereomers. The reason for this is because of what's called the endo rule. Now I'm going to describe what the endo rule is, try to draw it in 3D, and then show you a shortcut that some former students of ours came up with. So the endo rule states that the dienophile, in this case that methyl ketone, will line up so its electron withdrawing group is beneath the diene pi system. The dienophile will line up so its electron withdrawing group is beneath the pi system. What do we mean by that? Well, let me redraw the diene, and I'm going to draw it as if we're looking at it along its edge. There's the diene. It's got 2 methoxys on it. And it has a pi system. There's p orbitals on all 4 of those carbons. They're all lined up. Remember, that's what it means to be conjugated. Now, my dienophile, which is just this alkene, and it's got a methyl ketone on it, that methyl ketone can be sort of sticking outside that overlap, or alternatively, let me just redraw the same diene with the exact same configuration. There's that same pi system. Alternatively, my dienophile could point that ketone more underneath the diene, and that's actually what happens. That's the arrangement that we get. That's the endo configuration as opposed to the exo configuration. And it has to do with the fact that the dienophile has a pi system that's involved in the cycloaddition, but the electron withdrawing group also has a pi system, and that wants to overlap with the pi system of the diene. That's a abbreviated explanation as to what's going on, but it's enough to get us to what the product actually is. And speaking of, that's hard to see. Does that mean I have to redraw these things in this 3-dimensional arrangement to figure that out? No, let's learn a shortcut right now that some former Orgo students taught me. They call it the Pac-Man rule. So if you remember Pac-Man, Pac-Man looks like this, and they think of a Pac-Man as a chomping diene. So the Pac-Man rule says, first, draw the diene like a chomping S-cis diene, as if it's chasing the dienophile. Turns out that's how we've been drawing it in every example today. Now, in the video game from several decades ago and still alive today, Pac-Man chases after these ghosts. So the ghost is the dienophile, which is really just a pi bond, but it usually has electron withdrawing groups on it, and the ghosts are running away from the Pac-Man. So I'm going to point those electron withdrawing groups away from the diene. So there's my EWG. Now what's the point of this? Well, there's a lot of stuff attached to all those atoms that become sp3 hybridized. All 4 of those atoms that are involved in the cycloaddition become sp3 tetrahedral carbons, and they have the potential to be asymmetric. So if I put another electron withdrawing group down here, and then maybe other things, let's say A, and then B, and then I could even fill in everything else. Let me slide this over just a little bit. What else is on this? A lot of H's. I'm actually going to draw the H's in. There's an H pointing inward there. There's an H pointing straight up there. There's even 2 other H's pointing like so. And if you fill all those in and you draw your diene chomping away, chasing that dienophile with its electron withdrawing groups pointing away, all you have to do is look at the groups that happen to be pointed toward each other, and they will all be syn to each other. And let's go back to the example that started this off and prove that that works here. So if I go back to the original reaction in this example, let me clean up this spot, and I'm going to first annotate my starting materials and fill in all the hydrogens. There's a hydrogen on that carbon. There's another one there. And then just clean it up by getting rid of that plus sign for a second. There's an H there. There's actually another H there. And there's an H there as well. How did I know how to point this H here? Well, hopefully you don't think it's up here, because what's the geometry of that carbon? Well, it's an sp2 carbon that's trig planar, so it's going to have 3 domains symmetrically arranged around it. That's how I knew where they're pointing. It's pointing down here because the methoxy is up there. And I circle everything that's pointing toward the middle in this case, which are all hydrogens. So these H's are all syn, which means the things outside the circle are also all syn to each other. That's what that means. Doesn't mean toward you or away from you. It means in the same direction in space. And look what happened. The methoxy, and the methyl ketone all have to be syn to each other. Yep, that's exactly what we observe. So that's a shortcut to help you figure out what the product looks like on a 2-dimensional piece of paper, but the reason are these 3-dimensional arrangements and the preference for the endo rule. Okay, so that's the Diels Alder reaction. There's a lot of stereochemical features of this reaction. It's very selective for stereochemistry, regioselectivity, and just how we can form very nice 6-membered rings. It's a very useful reaction, and we'll see it a lot in syntheses as we finish up the course.